Hi there. Thanks, Sabine. Appreciate the introduction. The link for the book is on screen here, and it is really relevant to what we're talking about today. In fact, chapter 8 is completely focused on graphs and machine learning with a workflow that we're going to go through today that includes Neo4j and Spark. So for the next few minutes or so, we're going to talk a little bit about why graphs are interesting for predictions. We'll look a little bit into connected features and then a specific example around link prediction as well. Mark, is there anything else that I've missed here?
I think we're good. Again, I guess just to keep in mind that there are lots of potential uses for graph and machine learning, and we are specifically focusing on one of them for at least half of the presentation. But if you have other ones, they're probably applicable as well.
Wonderful, thanks. All right, so if we think about why graphs and machine learning just are kind of natural, I have an interesting example, actually two examples of a very different behavior. If you think about voting and you think about smoking, there's an interesting book that I'll show you here in a second that talks about one commonality between these two that are extremely predictive. And maybe you're not surprised to hear that that's actually relationships. And so knowing whether somebody may vote or somebody may smoke, knowing about their demographics, their economic levels might be important. However, more predictive is the network around them and whether the people in their network participate in those behaviors. And in fact, in the voting example, what they've found is that your friend's friends are even more predictive than whether your friends vote. So people who you don't even know are actually predictive of whether you vote or not. So really some interesting research on that, and you can find some of that research in this book called Connected. And what we're really seeing is that relationships are some of the strongest predictors of behavior. And there's a couple other books here that if you like books, recommendations like I do, that also talk about this same element of prediction of relationships. One's called A Friend of a Friend, really good if you're looking at using network science to find your next opportunity, and The Formula by Barabashi, who's extremely well known in the network science side. So, in sum, we pretty much know that relationships are really strong predictors of behavior, and graphs, of course, kind of naturally store information as connections or with connections. So whereas traditional platforms may look at storing things in a flatter format, that kind of limits how easily you can traverse through your network, and also requires that you aggregate and filter this information. Neo4j and native graph database allows us to do things much faster, traverse those relationships, and extract and use them more easily. Now, it's probably not surprising if you think about the popularity and growing popularity of machine learning and trying to use predictions, and how much relationships are predictive, as well as just how much our data is becoming more predictive, that the rise of popularity in graphs is kind of off the charts here. So if you look at this is a report from DB Engines looking at the popularity of different databases and different platforms for databases. And as you can see, that top green line, the popularity of graph databases are surging right now. So thinking about that and machine learning in general, just a quick pause to say, is when we talk about machine learning, there's a lot of terminology out there. And if we think about artificial intelligence, we're probably thinking about more of an end solution that is trying to make a decision or solve a task in a way that is probabilistic, but mimics the way humans make decisions. Machine learning is really where graphs can bolster what you can do, and machine learning uses algorithms to help computers learn a very specific way of doing something that's specific to training on some examples, and we'll show those today. And deep learning uses the multiple processing layers, usually a neural network to learn data representations, usually for features and classification. So we're going to focus on machine learning. That's where graphs can help you get better predictions today. And graphs are actually used in many data science applications. So you can see from this list, it's across the board, but things that we see a lot of application for right now and our customers are using are things like financial services, and in particular financial fraud. So that could be things such as anti-money laundering or fraud detection or other types of financial crimes. Drug discovery is another area. So as you can imagine, and we have a small example on this, but as you can imagine, trying to understand how to repurpose drugs that are already proved or tailor things to certain sets of the population is a very connected problem. Recommendations, probably no surprise, understanding the proper product or service to recommend to somebody, knowing who their connections are and preferences of their connections is extremely important. And profiling, of course, understanding what communities people belong to is very important. Cybersecurity, predictive maintenance, customer segmentation, all of these things really do apply very well to graph data scientists, data science, churn prediction, and search as well, and doing more master data management are other areas that we see a lot of interest in. So if we think about using graphs to improve our predictions, we're really able to give people a way to have more accuracy and find things they wouldn't otherwise find with the data they already have. So as we said, we know relationships are very predictive, so not using them doesn't make a lot of sense. So a lot of current data science models actually don't look at the network structure of our data, and they basically throw out relationships. And doing that, as we said, doesn't make a lot of sense if we know that relationships are highly predictive. And so we can add that back in, basically essentially give you more data with the data you already have by using graphs in your machine learning pipeline. So as a company, we believe that there are 4 areas in general that graphs are really going to enhance AI. Knowledge graphs to help people make better decisions and build applications that have more context. Accelerating machine learning, so just simply being more efficient about getting our data into our machine learning pipelines and sub-filtering and just being efficient about the way we build smarter applications. Today, we're going to focus on connected features. So we can give more context to the features we have in machine learning and increase our accuracy or our precision and our recall as well. Very much in the future, we're also looking at graph native learning and using graph neural networks. That's kind of an interesting research area that we think that the market will push towards in the future. So an area we're looking at. So let's take a look at connected features. Mark, did you want to run through some of these examples?
Yeah, let's do that. So the first thing, I guess, to answer is what is a connected feature. So this description that we've got in here, or this definition rather, works quite well. So it's effectively metrics that are based on connections. So somehow, like for example, working out the number of relationships that are going in or out of a node, perhaps we're counting the number of triangles or neighbors in common. And those are just 3 examples of connected features. Effectively, it's just features that are derived from a graph. We've got 2 ways that we can derive those features. And if you've attended any of Neo4j's previous webinars, you're probably quite familiar with the left-hand side of this diagram. So these would be features that are generated from a cipher query. They're often locally based queries, and they use a pattern matching sort of approach. So it might be, hey, I want to start from a person and explore something around there, and in this case, we want to come up with the number that we can use. And there's a sort of sliding scale over to the other side of this diagram, where on the right-hand side, we're talking about graph algorithms, which in this case are globally analyzing the data. So we're often taking into account a much bigger part of the graph than just that local subgraph around a particular node, but actually maybe even looking at the whole graph, or at least looking at a specified subgraph to work out some sort of computation, and then we're going to use the result of that as a feature. And so kind of closely tied with that, feature extraction and feature engineering kind of come together. The feature engineering is the idea of, okay, we need to work out what features are we gonna come up with and feed into our model. Feature extraction is the process of, okay, we need to write the query to get those out. And so on this diagram, we've got an example of a Game of Thrones graph where the colors are representing the cluster that nodes belong to. The size is representing the importance of the nodes. I think in this diagram, this is the PageRank one, but you could equally use another centrality algorithm. And so on the table, we show, okay, well, we might have a person, they might have some sort of, I guess, almost property-based information indicating what house they're in, what age they are, what gender they are. The thing we're trying to predict is whether they're alive. And then we've captured the graph-specific features on this feature matrix of the last three. So we've got the PageRank, the degree, and the community. And the idea would be that whatever machine learning model we have would be able to take in this matrix of values and come up with some models, in this case, predict whether someone is alive or not. And again, across all the examples, the idea is that right now we can't go and run like a machine learning model on a graph. So we've got to reduce the dimensionality of our graph into some numeric values that can be used by the matrix of tabular structures these algorithms expect to receive.
So the graph. Oh, go ahead, Mark.
No, go for it.
So the different areas of graph algorithms and the features that you can derive from them, there are 5 areas that are in Neo4j today, and that are both some of the more global classic ones and some more local ones. So community detection is the name sounds, helps you find how groups are clustered or partitioning options. Centrality is all about importance. So PageRank is a classic example, but there is betweenness and all sorts of other algorithms as well that look at the importance of particular networks, or excuse me, particular nodes in your network. And then pathfinding, kind of the foundational group of algorithms for graphs, really looks at finding optimal paths, and then tries to also look at availability and possibly the quality of those paths between things. There's also heuristic link prediction. So we're going to talk a little more about this one. And that whole category of algorithms look at the likelihood of nodes at forming relationships based on how close they are, based on some kind of a heuristic proximity. Similarity algorithms look at how alike nodes are, usually based on some kind of feature or property in common. Embeddings aren't in Neo4j yet and aren't in our algorithm library, but they're something we're working on that we'll be talking more in the future. And that basically learns the representation of your path or your topology of the graph itself, the potential of doing subgraph or entire graph embedding. So let's talk a little bit about link prediction, dive into that area. And link prediction really is looking at trying to estimate whether a new interaction is going to form in the future, or whether there's some unobserved fact that we're missing in our data. For example, we know by looking at a couple different groups. There's a great example of a criminal network evaluation where they use link prediction to try to estimate whether there are connections between criminal organizations that really are probably there, but we just haven't been able to observe it yet. So those are kind of the basic of what link prediction is. And I've got just an example here that's quite fascinating using drug and gene and diseases. And so this example is from het.io. They have an impressive decades of biomedical information integrated into a knowledge graph. And what they are trying to do is predict new uses for drugs, or rather drug repurposing, using the graph structure and then doing some link prediction. So they have a really great browser. You can actually go to het.io and play with this. This example here is looking at multiple sclerosis and IRF1 gene, and looking at whether there are connections there that aren't direct but are tertiary, and then they estimate some probability based on weightings of the paths onto whether there's a likely actual relationship there. So Mark, I think I'm having a little bit of audio trouble, so can you take over?
Yeah, so we effectively there are a bunch of approaches that we can take for trying to predict whether or not a link exists between two nodes, and we'll go into some of them in a bit more detail as we go through the talk. But once you've computed these metrics between a pair of nodes, you come up with a numeric value, and then the next thing we need to decide is what are we going to do with those numbers. So you'll receive some sort of number, and you can see on this diagram on the right, maybe we've got a number representing how many common neighbors a pair of nodes have, what the preferential attachment of those nodes is. And so there are two general approaches that we found in the research. The first one is on the left-hand side of the diagram. So this is that we run the algorithm, we get the scores, and then we set a threshold value and use that to predict a link. So, for example, we might say if a pair of nodes have a number of common neighbors more than 3, we'll say that they do have a link between them. And if they have less than 3, then we're going to say, okay, they don't have a link between them. And so you could do that. You could do that for any of the metrics. We could do create some sort of code that did that prediction for us. That works quite well if we have if we know if we can come up with a good threshold ourselves. That's a pretty good approach. But it tends to really only work if we just want to use one of the values. If we'd like to take into account multiple values, so if we want to combine the output from the link prediction, a link prediction algorithm, maybe we also want to use the community detection algorithms output, then it becomes more difficult because we've effectively got lots of different thresholds that we're using. And so if we want to combine them together, we want to use this right-hand approach. And so this is where we're going to focus for the rest of this talk. And this is the machine learning approach. So you can see here, this is the matrix that we've talked about. So we've effectively feature engineered some connected features. So in this case, common neighbors and preferential attachment on the diagram right now. We specify our 2 nodes, and then we have the final column on the right-hand side is the label. And in this case, we're going to be doing a binary classification where a 1 means, okay, those 2 nodes have a relationship between them, and a 0 indicates that they don't have a relationship between them. If it was a different problem where you were wanting to predict some sort of numeric value, like if you were trying to predict the house price, then that could easily be a numeric value rather than a label approach like we're doing here.
Great. Thank you, Mark. I think my audio's back, so I'll do a few slides and then hand it back to you on some of the details. So let's actually get into the example where we're actually trying to predict collaboration. So we looked at a citation data set. So this is a really interesting data set. It's a research data set, and if you do a search on Arnett Miller or Miner and this detail, you'll be able to find this data set. We actually used a subset of that data set with 52,000 papers, 80,000 authors, and 140,000 co-author relationships. So a pretty healthy data set. We use Neo4j to create our co-authorship graph and look at the connected features. So we use Spark and MLlib to train and test our models using a random forest classifier, which we'll dive into as well. So first, our link prediction workflow, we start, of course, with just getting the data together, aggregating the data and storing it as a graph. And we did that in Neo4j. And I think Mark, okay, I got a few more things on this slide. So our total model, as you would expect, and this is pretty generic for at least the blue boxes for all, what you would do in general for machine learning workflow. You'd start with getting the data together, and then of course cleansing it, modifying it, just checking that data out, and then getting it ready for machine learning, training it, evaluating your results. And as you notice from all these arrows going back, this is not always a straightforward process. There's usually a lot of iteration you have to do to tweak your models and your data as you're evaluating it, and of course eventually putting it into some kind of operational or productionizing it. So I think great, yeah. So Mark, I think you wanted to say a few things on this slide.
Yeah, so our first step is that we began with the graph model on the top. So as Amy said, we're using a citation data set. And actually, we're only really interested in one part of it, which is we've got articles, which is the node in the middle, and then we've got people authoring them. So those are the relationships coming out to the left and the right. So imagine this is an example of an article that has two authors. And for our link prediction problem, we need to create a co-authors graph. So effectively going to infer the co-authors graph by looking at the original graph and seeing where there were pairs of people who worked together. If they did work together on one paper, we're going to create a co-author relationship between them, and we're going to capture the year property, indicating which was the first paper that they collaborated on. So they collaborated on 3 papers in 2005, 2008, and 2003. Then 2003 would be the value on the co-author relationship, and the other 2 would be ignored.
Great. So after creating our graph, then of course we go into the modification and exploration, and you can think of that as for us in this example, we were able to identify kind of sparse feature areas, take a look at what might be interesting or not interesting in our graph, and then go through the feature engineering process and the extraction process to give us new graphy, if you will, features, but give us new features that might be more predictive. And more animation there. And then a couple of the graph algorithms that we used for that, just a few examples, because we did use several and we looked at several. Looking at link prediction itself, we found and we used 2 in particular. One, preferential attachment, which measures how close people are based on shared neighbors. And what this preferential attachment actually does is it actually multiplies the number of relationships to have in general, and makes an assumption that if you have a larger surface area of your network, you're more likely to connect in general to any other node. And the idea from network science is actually called preferential attachment, which is the idea that the rich get richer, or people that are more popular are more likely to become more popular, that you're just more likely to connect to a node that has a large surface area of their own network. The other algorithm we looked at was common neighbors, and that looked at triadic closures. So if you can think about that, that's how many possible triangles you might have with somebody else in the network. And that's kind of shown by the right-hand graphic. And the idea there is that if you have, let's say 2 strangers have a lot of colleagues in common or a lot of friends in common, it's more likely they're eventually going to get introduced than if they have no friends in common. So even if you're a stranger, but you have a lot of secondary or third friends, more likely to meet or collaborate. So we found that a really good link prediction algorithm to take a look at. We also looked at several community detection algorithms, community understanding algorithms. Triangle counting and clustering coefficients were really interesting to look at, and in general, those are pretty simple to run. In the graphic here, we're looking at triangles and the coefficient for for U, for the node U, and you can see that the triangles are pretty simple to run. How many triangles run through U? Clustering coefficient looks at the total number of relationships relationships for U versus the number of triangles, and it basically is a probability that somebody in your network, two people in your network, will be connected. So on the left, U's network, their neighbors have a 20% chance of being connected around them. We also looked at Louvain as well as some other community detection algorithms like label propagation that is intended to take a look at how things are clustered and identify optimal groupings of nodes. Louvain is also used to find hierarchies in general. We weren't looking for hierarchies, we were just looking for different, more fine-grained communities in this example.
Yeah, and I guess, Amy, on that previous one, the thing to point out is that the triangles there are not the same as the triangles on the previous slide. So on the previous slide, we were saying, okay, these are the triangles between the potential triangles between the two people, whereas this one is the triangles of one node on its own. And then the other thing is, if you go back one slide, if you want a very quick primer of link prediction, this link on the bottom left-hand side of the slide, the BMAs, the link is a really helpful one, and it has also really good diagrams. So you can see a couple of those in the top right-hand side here. So this is a really good one if you want to see what stuff is possible. Cool.
Absolutely.
You can carry on again.
Okay, and I think I'm going to turn it over for you to you anyhow to explain a little bit how we prep the material for machine learning. So good timing.
Yeah. So now we're on to stage 3, and what we need to figure out now is how we're going to get our data ready to pass into our machine learning model. And what we've got on the screen on this diagram right now is this would be the fairly normal approach that you might take. So you might have your data on the left-hand side, some sort of data frame representing where one column is representing a feature, the blue column representing the label in this case, and then we have multiple rows of data. We might use like the scikit-learn or a function in Spark that just does a random train test split across these columns. And then I think on the next slide we show how you might do that. And so for our example, maybe it's going to look something like this. So we maybe have our common neighbors, the preferential attachment, and then the label. And then if we go to the next slide, that splitting approach maybe uses this train validation split function in Spark, MLlib, where the blue ones are representing rows that are going to be used to train the model, and the gray ones are going to be used to test the model. So this approach is useful for supervised learning, and so that's what we're doing here. And the idea here is, can we build a model on some data, and it's going to effectively come up with some sort of way of predicting links on the test set. We're going to train it on the ones in blue, and we're going to test it on the ones in gray. You might think, so this is what we did originally. We thought, okay, this is probably fine. If we then go to the next slide, we see actually this is not so good, and it leads to a really, really high accuracy model because we've leaked data from the training set into the test set. Now you notice that we didn't actually, the data is not leaked in terms of the rows. The reason the data leaks is because the rows are not independent, even though they look independent. And on a non-graph-based approach to building that feature matrix, they would actually be independent. The problem we have here is that those features that we're computing, it could be that the computation of one of the values for the training set actually uses data or touches nodes that are in the test set. So we've actually gone and computed the value at the winner that use information that we shouldn't have been able to see. And so we need to take a slightly different approach to try and avoid being able to see data that we shouldn't be able to see. And so what it means is that we need to go, before we even build our feature matrix, we need to cut our graph. And the most common way is to do it based on time. So if you have a potential for doing a time-based split, this is the easiest way to do it. And so that's what we've done on this data set. And so by analyzing the data, we could see that there was kind of roughly a 65-35% split if we cut this art minor net data on the year 2006 and we train a model on everything before 2006, and we test the model on everything greater than including 2006. So the idea here is we're building a subgraph for the early part of the graph, and then we're building another subgraph for the late part of the graph. And the links that we try and predict come from those two separate subgraphs. So we shouldn't be looking across the subgraphs. And then if we go on the next slide, we can just see here's just a simple example showing what it looks like. So we actually build another projection on top of that cohort one we did at the beginning. And this time the top one is capturing the early relationships, and the bottom one is capturing the late relationships. One other thing to keep in mind is that, so we just go back, sorry, one last thing on that slide. So one thing to keep in mind when we're computing these features, when we're doing it for the training graph, it needs to only use to work out those values only based on the data that it can see in the early graph. But for the test one, because the test one is later in time, it's actually allowed to take into account the whole graph when it's computing the feature values. But still remember that the actual pairs of nodes that we're going to predict, they need to be in the late graph or the one after 2006. So that's the first problem that we need to keep in mind when we're doing graph-based approaches, which is a bit different than what we might be used to. And then the next slide has the other thing that we need to keep in mind, and this is a more general problem that you can have with machine learning solutions, but it does appear in link prediction, and this is the problem that there are way more negative examples than positive examples. What we mean by negative and positive examples is a positive example for a model that we're building here would be two nodes have a link between each other, and here's the set of features that they have. A negative example would be a pair of nodes don't have a link between each other, and here's a set of features between those nodes. So if we go to the next slide, we can see why that's the case, because the number of negative examples, or i.e. nodes that don't have a link between them, is a massive, massive number, and it only gets bigger as the number of nodes increase. So this formula here makes the assumption that we're not connecting nodes to each other, and so the number of potential maximum number of negative examples is the number of nodes squared minus how many relationships you have minus the number of nodes, and so it's significantly bigger than the number of positive examples that we're ever likely to have. And so on the next slide we can see that actually the problem is if we decide, okay, we're going to use all those negative examples when we train our model, we can just build a model, a very, very high accuracy model, in fact, that just says actually no nodes are linked together. And it will be really accurate. It won't actually be very useful because the problem that we want to solve is, do I know whether there's a link? And it's just going to say no every time. And so this diagram is quite a nice one for explaining that. And it would be if we're trying to predict the color of fish, based on this training data that we've got here, we should just always say that the fish is blue because like 20 times out of 20 or 20 times out of 21 we're going to be correct. And so what we need to do is we need to address that. And this is a general machine learning problem. It has to handle class imbalance. It's just that it's a very, very extreme version that we're having to deal with. And so the way that we deal with it on the next slide, we've got two approaches. We can either downsample or we can upsample. So downsampling, so these are taken from Chris Albin's machine learning flashcards, which are quite handy for explaining machine learning concepts. And so on the left-hand side, we can see the downsampling approach. So here the idea is we're going to take those negative examples and we're going to take a random subset of them and reduce the size of the negative examples. And then on the right-hand side is another approach where we're going to upsample the positive examples. So effectively, we're going to make the positive examples appear multiple times. In our example, we chose to use the downsampling approach, but each of them obviously has advantages and disadvantages. And I guess another thing to keep in mind is that although the maximum number of negative examples is really, really large, what we can actually do is we can reduce it slightly before taking this downsampling approach by just looking at nodes within the neighborhood, like of 2 or 3 degrees away from a node, from a particular node, to try and find the negative examples. And so this is covered in the papers that we several of the papers that we read, and those are linked on the link prediction section of the Neo4j graph algorithms documentation.
And Mark, you and I had an interesting conversation yesterday about the benefits or the downsides to each one of these. And if I summarize it correctly, I believe that downsampling, in general, we're throwing out information that might actually be very predictive. So, that's the downside of that. And then for upsampling, if you're just repeating sample information, so you're just duplicating maybe your positives, you're actually potentially you're duplicating information, and you might be actually moving towards overfitting your machine learning model as well.
Yep.
So next, we're going to take a look at training the model itself, the model we selected, and then taking a look at how we went through the training process. And Mark, did you want to talk to us a little bit about how we picked our classifier?
Yeah, so when we're picking a classifier, remember that before we talked about it needs to be a binary classifier. So we want to pick a classifier that's able to take in some data and come up with a label, in this case, true or false, where true is, hey, I've got something between these, for this row, and I've got 0 or false, indicating there's no link between the rows. And what we quickly noticed was that there was a lot of interaction between the features that we were coming up with. And so what that means is that when we say that features interact with each other, it means that they're very correlated. So there could be a big correlation between like the common neighbors value and the preferential attachment values that we've computed. And the problem with that is that several machine learning models make the assumption that each feature or each column that you give them are independent values, and there shouldn't be any correlation between them at all. And so that's not the case with link prediction algorithms, because a lot of them, as Amy described in some of those examples, they're based on like, what does my neighborhood look like? And so we're always actually using that same neighborhood to come up with some of the metrics, even though they may be different ways of computing it. You're still kind of using the same data to come up with those values. And so you'll end up with a node that has a high common neighbors, maybe also most of the time has a very high preferential attachment, for example. And so we need to pick a model that can handle that. And nearly all the research around or papers that we found on this would talk about using ensemble methods. And so the one that we've picked is called the random forest. And so you can see on this diagram, this is a model that uses lots of decision trees. So a decision tree is kind of like a really, really overfitted flowchart, effectively, where it trains itself on just subsample on a subset of the data, and it basically builds a decision tree based on that data. And then you have another tree that does it on a different subset of the data, or maybe a different set of columns, and another one, and another one, and you can kind of choose however many you want. And then the idea is that for each prediction, the random forest will say, hey, decision tree 1, what do you think we should do with this row? Decision tree 2, what do you think? Decision tree N, what do you think? And then we take the majority vote, and that becomes our prediction for that row of data, or in this case, that link that we're trying to predict. And then so on the next slide, we've got an example of the one that we built, and what does it mean? Like, what is a decision tree? And so this is what one looks like. It's actually effectively building a tree being a graph, effectively building a graph where at each node we can decide whether or not the criteria is true. So on node 0 here, we're saying, when we get a row of data, is the common authors less than 1.5? If it is, go down to the left-hand node. If it's not, go to the right-hand node. You can see we've also got some sort of internal statistics of the model underneath there. But if let's say, yes, it's less than 1.5, then we say, okay, is it less than 0.5? Yes, it is. And then we're down to node 3. Okay, that means it's false. Okay, actually, it's more than 0.5. Okay, cool. That takes us over to node ID 4. So that means it's true. And so you can see on this particular one, it's really, really sort of narrowly, like very, very overfitted on this left-hand side. On the right-hand side, it gets a little bit more interesting. So if we go down and say, okay, common authors is less than 2.5, then that takes us down to node 6, and we're now comparing preferential attachment. So this is just one decision tree, and you can see this one has only looked at like two of the features that we fed in, even though it's actually the decision tree from our final model, which has 8 or 9 different features. Is there anything to add to that, Phoebe?
I don't think so. And I think, you know, just a note to the people, we took that approach and then trained 4 different models. So we used multiple graph features, and we added on the graph features as we went through. I think we saw on the last slide the common authors, you know, feature that was included, but we used a model that just had common authors. And then we added in what we were calling graphy features. So we added in that preferential attachment and the total neighbors algorithms that we talked about. And then we added in.
I think we tried some other ones as well, but they didn't actually make it better. So we took them out again, and that's quite common thing.
Yeah, it was certainly iterative. Yeah, I think we tried quite a few. So yeah, these are the ones that we were found, you know, made us increasingly improve. We also took a look at the triangles and the clustering coefficient that we talked about, and we ended up having to do a min-max split on that. And Mark, can you explain why we did min-max split on triangles and the clustering coefficient?
Yeah, so most of the features that you see on here, we just have one number sort of representing almost representing the relationship between the nodes, so like a single number for the pair of nodes. So common authors is how many common authors does the pair of nodes have? So we've got one value. Preferential attachment is what's the product of the number of neighbors each node has. With the triangle and the clustering coefficient, those are actually run on node by node basis, and so you end up with 2 values. You end up with one for one node, one score for one of the nodes, and a different score for the other node. And so we need to come up with a way of how to represent that. One way to do it would be just to say, okay, I'm going to just have one feature called node 1 triangles, another one called node 2 triangles, node 1 clustering coefficient, node 2 clustering coefficient. The disadvantage of that is that now our model is kind of trained assuming that it receives data in a specific way. So let's say that the node mark always appears as node 1 in our training set, but then happens to appear as node 2 in the test set. The model is now going to be completely inaccurate just because of the order that the nodes appeared in. And remember, this graph is kind of an undirected graph. So if I am co-author with Amy, Amy's co-author with me. We're not storing 2 relationships between those 2 nodes, and so that's why we need to come up with a way to handle these node-centric values. And so this is one approach to doing it. We can just take the minimum, the score for the node with the lowest triangle value, and then the highest triangle value for the other node. That's one way of doing it. We could have created the product of the triangles as well. That I don't think we haven't actually tried that out. I'm not sure that it would make so much difference. You just need to come up with a way that the score itself is independent of the way that the data was fed into the model. And then the last one on the right-hand side is we then ran the graph through community detection algorithms. So label propagation, we were trying to find sort of more coarse-grained clusters. So how do nodes fit into clusters on a bigger scale? With the Louvain algorithm, what it does, which is really nice, is you can get intermediate clusters. So say, okay, this was the cluster after iteration 1, this was the cluster configuration after iteration 2, and so we took like the most fine-grained cluster, like what was it after 1 round, and so we were kind of using them to find different communities. So we were using label propagation to find, okay, what's the big communities that these nodes fit in, and then Louvain modularity we were using to say, okay, but on a finer grain basis, how do they fit? And the way that these feed in as features is we're not actually feeding in the label that they come up with, but we basically ask the question, are the 2 nodes that we're trying to predict the link between, are they in the same cluster? And we check. If they're in the same cluster, you get a 1, and if you're not, you get a 0. So that's how they fit into the model.
Yeah, you know, and Mark, I think that's a great example of, and maybe the slide in general of you know, having to play with your data, having to play with the different algorithms you might want to use as features, playing with the features themselves and how you combine them. And you can even see there on the community model, we use, you know, 2 different types of community detection And you'll see in the results that that they're both have influence, different influence on the results. And so when you're doing this yourself, you really want to play around with with the different ways of looking at the data. Many of these algorithms are built with domain background and history and certain assumptions. If you're using a centrality, trying to find an influence of certain things, you may find that just because the way the algorithm assumes that that it's looking at the data, that you get different results, because influence, for example, can mean a lot of different things. Even community, like, well, what kind of community? How fine grain of community are you looking for? So definitely, play with the data, as you and play with the different algorithms as you work your model. So next, we are going to look at evaluating the results, and we did that in Spark. And as far as just as what we use to evaluate the results, we use the basic measures that you would see in most machine learning papers. I won't walk through all of these in detail. I always have to remind myself, which one I'm looking at and what I'm looking for. But the thing here to take a look at is, for example, on precision. A low score might mean more false positives. On recall or true positive rate, a low score might mean more false negatives. So you might have a goal to optimize for one of these versus another. In general, a higher number is better. Getting your accuracy and precision in a recall, at a higher rate means a better predictive model. But you also want to tune it for maybe something you're particularly sensitive to in your predictions. What we looked at is actually the ROC curve and the area under the curve as well. And you can think of the ROC curve as just an XY chart mapping the true positive rate and the false positive rate. So that's what we're going to visualize. And then, of course, we looked at the accuracy, precision, and recall separately as well. So our first model, when we ran that, you can see here the green line compared to the random score, which is the blue line. It might, our accuracy was 86% there. So you might think, well, that doesn't sound too bad, but actually 86% is actually not very good at all. And I've circled this area up here where you would end up with a lot of false positives. So if you kind of think of that as, if I want to get to 80%, so you can see on the left there your true positive rate, if I want to get to even at an 80% rate or just above 80%, I guess I'm saying 86% rate of true positives, I'm going to end up with a whole bunch of false positives as soon as I reach anywhere above that. And that can be really problematic for something like fraud detection. If you have a bunch of false positives in fraud protection, your team is going to be running all over the place trying to track down things and stop transactions that really should go through. And that's actually really a problem for a lot of our customers, because it can be quite expensive to track a lot of false positives. Now, this result actually has all four of our models mapped to it. And you can see that we've increased, by the time we get to model 4, we've increased our all of our metrics. We're in the high 90s here. And you can kind of see that as the purple line here, kind of up and to the left, where we've increased it considerably. Mark, did you want to say anything about this, process of evaluation and looking at these different models?
Yeah, so I guess the ROC curves tend to be the sort of way that people. So what we were finding was, when we were researching the link, looking at the link prediction sort of materials, this was the common way that people were measuring. Effectively, every paper tries to say, hey, I've got a way of predicting links. It's better, and that's my addition to the field. And all of those are based on these area under the curve diagrams that we've got on the left-hand side of here. I think if you were building this for an actual application, so like if we were trying to, if Amy and I were building some sort of application based on that collaboration network, And the way that we actually wanted to use this model was, hey, I want to try and suggest some people that a person might like to collaborate with when they log into this application. Then you'll find that the accuracy, recall, and precision values are much better. And depending on what type of error you can handle, it could be that you actually try and max out one of the scores, even if it decreases the other one. The other thing to keep in mind is, although you can get very high scores on this data set, there are certainly other link prediction problems where a much lower score than this would still be considered really good. It sort of depends on whether the topology of the graph predicts the future topology of the graph.
Great, thanks. And then just thinking about, iteration and tuning, as we've been talking about, is feature influence. So for Spark, there's in the random forest, you can get an average in the reduction of impurity, and that's across all the trees in the forest, and give us a ranking of how much influence a particular feature had on our model in comparison to the other features. So if you were to remove one feature, it would still normalize. So looking at this, you can see common authors was very predictive. But as we remember from the beginning, that still, using just that, only gave us about 86% accuracy. So not enough on its own. Being in the same partition of that finer grain community for Louvain is kind of next up. So another community detection, same partition, which is using label propagation, also very predictive, and you can kind of see some of the other metrics as well. If we were tuning this for some kind of application, as Mark said, we might try removing different features and see what happens, because we wouldn't want to have having a lot of features can also cause you to overfit your predictions to just your training set, which makes it hard to apply to other applications. So you might want to try to remove some of the less influential features, or remove maybe one of the more influential features and see what the stack rank changes there. The other thing that we've seen people do is using PageRank on the features to actually estimate influence as well. We didn't actually run that, but it is something that the people are also doing. So there's a lot of things to kind of try out and see what kind of results you get, and tune it for, as Mark said, maybe one of the, maybe recall is more important for you, and the other metrics, if they're low, doesn't matter. So a lot of tuning and playing to do. And I think basically, here we go. Here's just a final overview of the process that you could use. You could plug in, your own tools. Maybe maybe you want to use different different platforms to do your training, whatever that might look. So this is just a generic machine learning workflow, and where Neo4j would fit, and it would you could plug in different examples there.